Everybody. So again, sorry I couldn't make it to class today. What I thought I would do is make a couple of videos that will kind of fill in for what we would have gone over in class today. And maybe we won't get through quite as much information, but hopefully we can at least do enough that we kind of stay on schedule and don't fall behind and make the last few weeks in this class miserable. So the idea is maybe I'll kind of come up with some class notes for today. Today being what, the 15th? And what I want to do, I think I'm going to send you two separate videos. So in this video, I want to finish up what we've been calling 1.6 part 2. And so that's what we talked about in class last time I saw you on Wednesday. And maybe I'll write kind of continued out here. We got through almost everything. The idea from 1.6 part 2 is I want you on your calculator to be able to make a histogram and to be able to make a box plot. And then not on your calculator, be able to make a stem and leaf plot. And kind of understand what those three things show you, those different pictures. And that should be what we went over in class last time. One thing that I want to add to that, so also from 1.6 part 2, is this concept of shape. So I'm going to talk about shape for, I don't know, 10, 15 minutes, something like that. Then I'll flip through the homework, and then I'll call this video good. And this will, at the end of this video, that'll kind of cover everything that we'll have on our quiz this week. But I'll send you information about that. So anyways, shape. The idea with shape, I think it's easiest to think about it in terms of a histogram, right? So if you made a histogram, and I don't want to draw out a histogram because it's kind of a pain, but maybe you could sort of imagine a histogram that sort of has a shape that looks something like this. Like that's not a histogram. Histogram's got like little bars of different height, right? So maybe there's a bar from here to here that has a height like this, and there's a bar over here that's not as tall, and maybe that's roughly there. And what I drew in blue isn't exactly what I'm drawing in red, but maybe the idea is blue kind of sort of approximates what you see in red. It's not perfect, but I want to draw something in blue that'll work for a lot of different histograms that you'd see in red. So anyways, I want to draw for you 4 different shapes, and then kind of the goal will be you'll make a histogram. I mean, exactly what you're going to do on this quiz is I'm going to have you make a histogram, and then I'm going to ask you about the shape. And it won't look identical to any of these 4 shapes, but it'll look pretty close to one of the 4, and you'll identify it as one of these 4, and then you'll get full credit, and you'll be really happy. So the 4 different kind of shapes that I want you to be able to recognize in this class is this one that I already drew, one that kind of looks like this, roughly speaking, one that, I don't know, kind of, sort of looks like that, roughly speaking. And then this last one here, which is by far the least important, which just sort of looks like this. And they all have different names. Frankly, they're going to be in order of importance. This one's going to be the most important. These 2 kind of important. This one not important at all. I'm going to talk about some of their characteristics, their names, that kind of stuff, and we'll move on. So this first one, kind of annoyingly, has several different names. Sometimes it's referred to as Symmetric Bellshaped. And the idea with bell-shaped, they're talking about like old school bell, like Liberty Bell or whatever. You can kind of picture a bell here, like the little, I don't know, bell thing that goes, that's dumb. This is the outside of an old bell, I guess. Symmetric bell shape is the way this shape is often described. Although what you'll see is we're going to move beyond that and we're going to call it something a little bit different. So maybe I'll write AKA. Later on in this class, we're going to refer to this as approximately normal. And so it's kind of just semantics, the difference between these descriptors and this description. This really refers to the distribution itself as opposed to the shape of the graph, but you don't have to worry about any of that stuff. Right now, when you see something like this, if you want to call it symmetric bell shape, that's great. If you prefer to say it's normal, or maybe more accurately, it's approximately normal because it's not exactly normal, yeah, we'll call that good too. Either one will get you full credit. You might wonder why this one's so important. I think I made the case that this is the most important of the shapes you'll be looking at. The reason why is because it ends up occurring a lot. It occurs in nature, it occurs in sciences, and even if you have histograms, data that would not have this shape, very informally speaking, we're going to learn a way to kind of make them have this shape, I guess, later on in this class. So this will be the shape that we study the most, this approximately normal distribution. We're going to get really good with this. We're going to spend a ton of time here. Some examples, I think I Googled something like, I don't know, approximately normal examples, and here's one of the histograms that popped up. So apparently this is something that somebody made, took 101 US adults and figured out their BMI, their body mass index. And most people are in here with the BMI between, what, 22 and 28 apparently. But not everybody. Some people have lower BMIs, some people have higher BMIs. You kind of get this shape. And I know this histogram that you see here is not identical to this curve that you see here. But hopefully, if on a quiz I had you make a histogram and it looked like this, you'd be like, all right, that kind of looks like this. It doesn't really look like either of these three out here. Maybe process of elimination. Body mass index is something per this histogram that might have this approximately normal distribution, this symmetric bell shape. There's nothing special about that. I just kind of Googled and played around and found lots of different things that have that shape. Some that fit it pretty well, whatever this is a picture of. Some that don't fit it quite as well. Often you see the approximately normal shape kind of overlaid with the histogram itself. And I mean, you can do this if you want. You can Google and you see lots of different places it comes into play. I thought this one was kind of interesting. These are stock market returns. And so I don't know how much you know on finance, but generally people think of the stock market as this really volatile thing that's impossible to predict and blah, blah, blah. But actually, there's a lot that you can predict. The approximately normal distribution tells you a lot of stuff. What this is doing is it's taken 50 years worth of data. And the 50 years changes is why the histogram's changing. Right now it's these 50 years, but it changes it. And it keeps track of returns. How much money you made on average on, I don't even know what this is talking about, a bunch of different stocks, I guess. And most of the stocks make somewhere in here, but some make significantly more and some make significantly less. And all the different red histograms, which are changing because the data is changing, maybe you can kind of see how they kind of sort of fit this approximately normal distribution that we have here. Which is sort of wild when you think about the stock market as something that's impossible to predict. And I'm going over a 50-year period, and we have all these different highs and lows in the data, Great Depression. I guess this is after Great Depression, but you get the point. Anyways, the approximately normal distribution ends up fitting things that you wouldn't think it would fit. Stock market returns, for example. 3D printers, how accurate they are, right? You're supposed to make something that weighs exactly 30 grams or something, and you use a 3D printer. And it's not, maybe it's not perfect. Maybe it makes something that weighs 30.03 grams, a little bit more, a little bit less. End up following a symmetric bell-shaped distribution. Accuracy of telescopes back in the day when people were trying to make predictions about planets and their orbits and stuff. I mean, just all sorts of really weird cases. Female shoe sizes, apparently, of adults follow symmetric bell shape. And nothing special about female, you just want to control for gender. You end up having a shape like this. The point of all this, I should probably stop talking about it, is that this is an important shape. And you're going to want to recognize it a lot. It's called the approximately normal distribution, and you can describe it as symmetric bell shape, and it kind of, sort of looks like this. All right, the next two shapes that I want to talk about over here, which I'll spend less time on, they're what are called skewed. I'm going to leave a little bit of room there on purpose. So these are both skewed. One of them is left skewed, one of them is right skewed, and the most common mistake Math 243 students make is they confuse the two of them, and I'll teach you how to do that, but how to recognize them. But before I do that, I just want to kind of talk about them a little bit. With this symmetric bell-shaped distribution, I sort of have most of my observations kind of in the middle, informally speaking, but then it's equally likely that I'm higher or lower than that middle here, right? Most of them cluster around the middle, but some are higher, some are lower. Most females have shoe sizes between, I have no clue what numbers those are, 5 and 10 maybe, but some females have shoe sizes of 11 or 12, and some have shoe sizes of 2 or 3. I don't know if that's true at all. I have no idea what size shoes females wear, but the point is it's supposed to have a shape like this per something I read on Wikipedia. Over here I have a very different picture. Over here, most of my observations are over here on the left of my graph. But some of them are significantly more than that. I have this big tail going out to the right. I don't have this tail to the left. Most of my observations are on the left, but then I have this big tail to the right. And this is supposed to be kind of the analog of this one where most of my observations are over on the right, but I have this big long tail to the left. They're both skewed as opposed to this one, which is symmetric. The way you recognize them is you think about the tail. So this tail that points out to the right makes this one right skewed. And this tail that points out to the left makes this one left skewed. And these distributions will be less important than this distribution. In fact, we'll learn if we have these shapes how to change them into this shape. But I do want to talk about these just a little bit. So with the right skewed distribution, the classic example, the one you'll see way more common than any other one, which you will likely see in this class at some point, is income. If you think about household income, right? Maybe, I don't know, 100 grand is right here and 200 grand is right here and 300 grand is right here and so forth, right? Most people make between 0 and 400 grand. Most people do. I know I'm certainly in that 0 to 400 grand range as far as annual income goes. But not everybody, right? Some people make significantly more than that. If you think about where Steph Curry would be if you made this histogram, there's people that are way out here to the right. I have most of my observations over here on the left, but I have this super long tail out to the right for people who make millions and millions of dollars in a given year. Right? When I talk about household income, that's something that's very clearly right skewed, and that's the example that we will use for something that's right skewed often in this class. Other examples that I've seen before: age of students at SOU. How old you are when, I don't know, you graduate from SOU maybe. Most people graduate SOU, what, like between 20 and 25 maybe? But not everybody, right? Some people maybe served in the military and came back to school, or worked for a while and then came back, or did whatever else they're referred to as non-traditional students, students who graduate significantly later. There's probably people that graduate SOU in their 80s, right? Most people are between 20 and 25, but some are way out here to the right. You don't see anyone graduating SOU at 3 years old. I don't have a tail to the left. Most of my observations are on the left, but there's this big tail out to the right. So the age that you graduate college could be something, for college graduates, could be something that shows up over here. That's probably enough examples, but maybe I'll move on to left skewed. Generally, left skewed is harder to come up with examples of. The idea is most of my observations are over here on the right, but a few give me this big long tail out to the left. A few are significantly less and create this tail off to the left. The example that I like the best over here is age, mortality. I don't even know how to describe it. How old somebody is when they die in the United States. Right? And it's kind of a morbid example, but it illustrates the point pretty well. Maybe this is 50 years old right here, and this is 100 years old right here. Right? So there's 50 and there's 100. And most people live to be between 50 and 100 years. And you don't really have anybody much more than 100 years. Like nobody's 150 or whatever. There's probably somebody who's in their 110 or something. But there's not really too many people to the right of this huge chunk. But sadly, there's a bunch of people to the left. Right? Like infant mortality is a thing. People die in car crashes in their teens. Like people die when they're really young. It's tragic. It's super sad. But it creates this tail going out to the left. You don't have a tail out to the right. How old somebody is when they die in the United States of America would be something that we'd expect to be left skewed. Anyways, there's a little bit on skewed. This last one I care even less than the skewed ones. This is what's called the uniform distribution. I care very little about this, but I think it shows up on the homework once or twice, so I want to mention it. The idea for a uniform distribution is the height of the different bars in your histogram. If you want to picture those here, they're all about the same, give or take. So something that it's equally likely that I fall anywhere in this range ends up being what's called the uniform distribution. We will talk about that very, very little for this quiz this week. Expect to distinguish between the three of these guys right here. And when I say distinguish between them, there's really two different things I want you to be able to do. What I'm going to ask you to do with 100% certainty is make a histogram. And I'll probably ask you about the shape of that histogram. And then you'll just recognize it as such. The more advanced level stuff that you'll get some practice on the homework, which may or may not show up on your quiz, is if I just describe a situation like the age of students at SOU. What are old quiz questions I've given? One I remember is how many math classes college graduates have taken, right? So you figure most people, when they graduate college, have to take 1 or 2 math classes to fit that kind of quantitative reasoning box. So most people, I don't know, 0, 1, 2, 3, something like that. Depending on your major, your computer science, you got to take 4 or 5 maybe. Oh, but then there's some people that really like math, right? Like me, kind of. You're a math major maybe, or math minor. You had to take 10 or 12 or 20 classes. If you can think about which of these shapes that situation would describe, where most people take 0, 1, or 2 classes, but some take significantly more, right? 5 or 10. If you recognize that as a right skewed distribution, that's fantastic. And it would be, because 0, 1, 2, 3, right? Maybe it would look something like this, but there'd be some way out here to the right. You can't take negative 10 math classes, so you don't have this tail out to the left. It would definitely be something that's right skewed. Easiest way to identify the shape of a distribution is with a histogram, but it's worth pointing out that you can do it with a box plot as well. So if I'm in this symmetric bell-shaped case, aka this approximately normal case, I kind of have most of my observations somewhere, and my median is kind of in the middle here. Remember, this is my 25th percentile, my 75th percentile, the first and third quartile. And then some observations are less than that, maybe, I don't know, like this, sure. And some observations are more than that. And I have this nice symmetry going on here, right? These whiskers are about the same length. The median is kind of in the middle of the 25th and the 75th percentile. If I made a box plot of data that was approximately normal, I'd expect it to look like this, which would be very different than a right skew distribution where most of my observations are collected over here on the left. So what that means is my box plot would look something like this. What's going on here? Most of my observations are over here on the left. I don't have this tail out to the left. But some are significantly more. Here's my median. My third quartile is way over here. And then I have this huge tail out here. Maybe I even have an outlier or two. Who knows? Maybe it looks kind of like this. This would be a right skew distribution. And a left skew distribution would just be this guy kind of flipped around. So I have this huge tail now going out to the left. But most of my observations are sort of clustered over here on the right. This is what's called a left skew distribution. And a uniform, it ends up looking a lot like the approximately normal distribution. These end up being a little bit shorter, but I don't even really want to get into that. I'm never going to ask you to identify a uniform shape from a box plot in this class. So if you recognize that this one's approximately normal, that this one is right skewed, and that this one is left skewed, and you can get it from either the box plot or from the histogram, that's fantastic. And I think that's everything I need you to know about this shape. And again, the more expert level is when it's described in words, but maybe we don't put that on this week's quiz. Maybe we save that for the midterm or something like that. But you will see that in the homework, and actually that's what I want to do now. I want to take a quick look at the homework and then I'll end this video. So here's your homework for this week. And it's supposed to cover 1.6 part 2, so not only what this video just covered, but also last class. And what you'll see is it's not perfect. I mean, what I'm going to ask you to do on this quiz is make a histogram, make a box plot, and I want you to be able to do both of those on a calculator. So like specify the bin size and X min and X max and all that kind of stuff. More on that later. But you can't really make a histogram on these online homework systems. So instead they kind of multiple choice their way into it. So what this is saying is observations between 2 and 7, there were 2 of those. Observations between 7 and 12, there were 5 of those. Observations between 12 and 17, there were 6 of those. This is what ended up happening. And then you made a histogram. What would it look like? Which of these guys? Hint, it's not this one. Why? Because here, observations between 2 and 7, there's 3 of those. And this says observations between 2 and 7, there should only be 2. So it can't be this one. Maybe you can process of elimination your way into which of these it ends up being. A comment here, this is what's called interval notation. So the bracket means this includes 2, but the parenthesis means it doesn't include 7, which is exactly the standards we've been following, right? This says 2 to 7, but really it doesn't include 7. 7 goes in this box here. So ties go in the bigger bin. So that's what this interval notation indicates. And I talked a little bit about what I want you to do is make this on your calculator. Make sure you can specify the window on your calculator. So for this one down here, for example, the X min would be 2, the left endpoint of your smallest bin. The X max would be 27, the right endpoint of your largest bin. And the X scale would be 5, which is the length of any one of these bins, the distance from 2 to 7, for example. Those are really important. The Y is less important, but I'm going to ask you about it on the quiz. Y min, you can always put in 0. Y min is just referring to what you see here. So in this version, Y min is 0, Y max is 6, and Y scale is 1, how far apart these guys are. So this one, to give you a little contrast, Y min still 0, Y max would be 8 now, and Y scale is 2, because these are 2 apart. For our class, Y min can always be 0, Y scale can always be 1. And Y max, just make it big enough that you can see the tops of each of your different bins. Anyways, on this homework question, multiple choice, figure out which one this is. Second one, kind of the same idea that give you the histogram already. And by the way, I think we'd say this shape is approximately normal. And you're like, it's not exactly this shape, but it's closer to that than any of these guys. This being a little tall might throw you off. If I was making this on your quiz, maybe I'd change things a little bit so it looks even better, so it's more obvious. But this doesn't ask you anything about the shape. It just asks you to interpret it. So interpret the third bin. This one right here. This bar that you see right here. What's that tell you? Does that tell you that there's 7 snacks that contain exactly 95 milligrams of sugar? Or does it tell you there are 95 snacks that contain 7 milligrams of sugar or something else? Read through these. Hopefully you're able to figure out what that's telling you. Third question, they give you a histogram and you're supposed to figure out the shape. So note that the 4 choices you have, uniform, bell-shaped, skewed right, and skewed left, correspond pretty closely with these guys that I called them here. Uniform, skewed right, skewed left, and bell-shaped. Bell-shaped, I guess. But the point is, look at this one and you notice most of your observations are over here on the left, but you kind of have this little tail going out to the right. And maybe that can help you figure out which of the shapes it is. And that won't necessarily be yours. This histogram will randomly change, but it should change into something that looks kind of like one of these four. Fourth one, they give you the histogram and they ask you some questions. They ask you for the class width. And if you have your notes from Wednesday, you'll see that class width means the exact same thing as bin size. So that is what you put into the X scale part in your window. So for here, X min is 1, X max is 25, and X scale is 4. And so since the X scale is the bin size, aka the class width, I guess I'm telling you the answer here is 4. And this is kind of a weird question, sample size. They're just saying how many total observations did you have? Well, I had 2 in here and another 10 in here. Maybe you can add up a bunch of numbers and figure out what your sample size was. Question 5, I like this one. I think this is a really good question. Here is a box plot, and they ask you to kind of interpret it. So I know it doesn't look exactly like the box plots that your calculator gives you, but hopefully it looks close enough. So you got your median over here, and your third quartile, and your first quartile, and there's no outliers in this case. This is your smallest observation. That's not largest observation that's not an outlier is what, 19, I guess. And the smallest observation that's not an outlier looks like it's 1. And they ask you a bunch of questions. Is this skewed right? I don't know, maybe you can go back to this and take a look at what a skewed right box plot would look like and figure out whether it looks like that or not. Is the interquartile range about 8? Interquartile range, that's not directly on my box plot, right, but Q1 and Q3 are. And so maybe you can ballpark Q1 and Q3 from looking at the picture, and once you know Q1 and Q3, you can ballpark the interquartile range. Median, that should come straight out of your picture. Maybe you can figure out which of these statements are true, and then answer down here. I think this is a good question for what that's worth. Question 6. Now we're getting into stem and leaf plots. Look a little different than I made them in class. This weird pound sign here you don't have to worry about. But the idea is to make a stem and leaf plot from this data. Oh, that sounds like a lot of work. Yeah, it is. So they did a bunch of it for you already. Right? This 2 right here means I have an observation of 12. And this second 2 means actually there's another observation of 12. And all you're supposed to do is fill in the leaves for this stem of 4. And there's no reason you couldn't do all of them, but it just seemed like a lot of data, so they have you do that. Question 7, more on stem and leaf plots. The idea here, and maybe this is kind of clever, is they don't even give you the data, but they ask you for a 5-number summary. How the hell are you going to make a 5-number summary if you don't have the data? Well, fortunately, you have a stem and leaf plot. So maybe from the stem and leaf plot, you can get the data. If you have the data, you can put that into a list on your calculator, and then you can do 1 variable statistics to get these 5 numbers for your 5-number summary. And the last question, hardest question on here, this is all about shape. And the idea about shape here is they're going to describe a situation, housing prices, where a quarter of the houses cost less than this amount, half of them cost between these values, and there are a meaningful number of houses that cost more than this amount. Reading those numbers, thinking about where they'd be on a histogram, maybe that can help you figure out whether it's symmetric or right skewed or left skewed. And one other thing that I didn't tell you that's really important. So it's a weird time to be telling you, but let's go back to these class notes. If you think back to 1.6 part 1, we talked about there are different measures of center, the mean and the median. And there's different measures of spread, the standard deviation and the interquartile range. And what I told you is that sometimes you use the median, and I'll write these down. Sometimes you cite the median and the interquartile range. And sometimes you cite the mean and the standard deviation. And I put this on your quiz last week, and then I felt bad because a lot of people struggled, so I told the grader to make it extra credit. You'll see that soon enough. So when do you cite which? Well, what I had told you before was that we're going to use median and interquartile range when we're worried about outliers, right? Because these 2 measures are what are called robust. So they're not influenced, or they're resistant to outliers, whereas the mean and standard deviation aren't. So when you had outliers, use the median and the interquartile range. When you don't have outliers, use the mean and standard deviation. That was kind of a simplistic approach that we learned when we first took it. We're going to take a slightly more sophisticated approach now. And the idea now is it's not whether you have outliers or don't, it's whether you're worried about outliers or not. And if your data is skewed, you're worried about outliers, which kind of makes sense because you have these tails, either a tail out to the right or a tail out to the left. And if you have these big long tails, you have observations that are significantly different from the majority of your observations. So when you have skewed data, You're worried about outliers. When you're worried about outliers, you're going to cite robust measures, the median and the interquartile range. And when you're not worried about outliers, in other words, when your data is symmetric bell-shaped, approximately normal, you're going to cite the mean and the standard deviation. And so going forward in this class, anytime your shape is skewed, right or left, and I ask you, what's the measure of center, you're going to say the median. What's the measure of spread? You're going to say the interquartile range. And if your data is approximately normal, aka bell-shaped symmetric, you're going to cite the mean and the standard deviation. And what if it's some other shape? What about uniform? What? Don't worry about it. It's going to be one of these three. And if it's these two, you use these. And if it's this one, you use that. And that was really the last thing I want to talk about from 1.6 part 2, even though I forgot to. And that will allow you to answer this question. If you decide that this is describing something that's right skewed, I'm not saying it is, but if you make that decision, well, if it's skewed, I'm worried about outliers. If I'm worried about outliers, I want robust measures like the median and the interquartile range. And you'll note on this question, they give you another scenario later down. And maybe you think this one's symmetric, in which case you'd use the mean and the standard deviation. Again, I'm not saying it is. You got to read through these and figure out what they are. And I think you do that 3 different times, maybe 4 different times. And that's the last question on your homework. And I want you guys to decide the due dates on your homework. So maybe we'll wait till Wednesday to officially assign this. But I'm kind of thinking like later this week, maybe tentatively like Thursday or Friday of this week. So if you guys could start this homework assignment, and then maybe next time I see you, we could actually figure out a due date and see if people have gotten stuck on anything. I think that'll help keep us on track. So I'm going to end this video now because I want to make a second one, and this is already getting kind of long. So I'll stop it here.